Today I'm going to talk about work that I did together with Adama Kepi, Aaron Oradou, and Karin Gouache, I think came off from different universities, research centers in Paris. It's about the dispersion and modeling of dispersion of motile bacteria in porous medium. We model the experimental data of a paper by Adama as first author on which I'm showing. So this is the experiment that has been done at the FAST laboratory in Paris. So it's like a Haley short cell in which you have pillars, circular pillars. This is the model medium. And then, so this is these white spaces that you see here. And then there is a water flowing through. And different colors here indicate different flow speeds. That's the absolute value of the velocity. And these lines that you see are the trajectories of bacteria. So they can, with a microscope, you have to, it's a very narrow cell, but still with a microscope you have to focus on a certain plane that you have, which is in your focus. And then you can follow trajectories of particles of bacteria. And this is what they have done here. And so here you see bacterial trajectories at different flow rates. It's the same medium, but once we have a flow rate that corresponds to an average bacterial velocity of 98 micrometer per second, and at the bottom 43 micrometer per second. In total, we have considered 1, 2, 3, 4, 5, 6, 7 data sets, different flow rates. And so what you see is here already a qualitative difference between the trajectories. So for the higher flow rate, the bacteria have relatively straight trajectories, but they make excursions. They like to go towards the grains. But for the lower flow rate, this occurs much more often. So bacteria. So you see, so here the bacteria would follow a streamline of the flow field, but then it starts to move. This is the motility of the bacteria. It has a flagella, with which it can move, and typically what bacteria like to do is they like to go to areas of high shear, high flow shear. And the high shear is close to the grains. At the grains, you have a low slip boundary, so this is where the shear of the fluid, of the flow is maximum. So bacteria like to go to high shear areas. Why? Why? Yeah, that's a good question.
The answer was always evolution.
Yeah, very good, exactly. There must be, well, I mean, you can imagine, there must be some kind of advantage. Also, maybe there are nutrients around the nutrients accumulating. Not here. No, here we have only the bacteria and the water. There is no chemotaxis or anything, but it's pure, what we call rheotaxis. So the bacteria, they swim, but then there's an interaction with the flow field. So rheotactic, it goes towards the high shear. On some flow rates, it also goes towards low shear. So you can see different types of behaviors. So here, what we should say, so these are some data from the experiment. Pillar diameter is 35 micrometers. We define a characteristic time for attraction of the bacteria, which is the pillar diameter divided by mean flow. And the swimming velocity of the bacteria themselves is about 12 micrometer per second. So if you have the bacteria in, let's say, without a flow field, just with the fluid, that they move by moving the flagella. And you can measure the flow speed. So in principle, this type of motion, where they just move the flagella, is kind of a diffusive motion. It has a mean zero, a mean displacement of 0. From the displacement variance, you can estimate the velocity. And the characteristic velocity is about 12 micrometer per second. So you see here the lowest flow rate is on the order of the swimming velocity. no? The lowest mean velocity. So what we measured, so what we want to do is we want to characterize this motion of the particles. No? And motion is attached to the velocity. So what we measured was the particle speeds. So we look at the absolute value of the particle motion. So to do this, you just look at the bacteria position at a certain time t, and then at a certain time delta t. And then you look what is the displacement between the two measurement times, and you divide it by the time increment. This gives you the velocity of the bacteria. And there were two types of bacteria, non-motile bacteria, they were dead, they just didn't move, and motile bacteria, the one that moved the flagella. And for the non-motile bacteria, if we rescale the velocity, the speeds, and the PEF, the probability distribution function, with the mean flow, they all collapse more or less on the same graph. This is good, because it tells us that they are basically transported in a passive way, because then we scale with the flow speed, or with the flow rate. So in this sense, we can use the non-motile bacteria speeds as a proxy for the flow speed. But of course, I mean, these non-motile bacteria, they also have a certain size, and they cannot go arbitrarily close to the grains. So they cannot explore the very, very low velocities that you have close to the flow, to the no-slip boundary. When we look at the motile bacteria, and we rescale them also with the mean velocity, they collapse relatively well, but not quite, not as well as non-motile bacteria. And so what we see is that, particularly at the low flow rates, the speed PDF is shifted towards lower velocities. This is because they like to do these excursions towards the grains and to the weight of the grain where the velocity is very low. So the motile bacteria, they're not really faster, no? It's not that they swim together with the flow. Now, really, what happens is the bacteria velocity is reduced, because they swim towards the grain and then they get trapped when they move around the grains. And this is what you see here. The smaller the flow rate, the more the velocity gets reduced with respect to the mean flow velocity. This the black line here is this gamma distribution that we fitted to the non-motile speed distribution. So now, I mean, this is clearly, I mean, the deviation here from the non-motile is of course an effect of the motility. So now, what we considered were different observables. So how do you measure, how do you quantify the motion of the bacteria? So we did this, we said, let's look at the displacement distribution. So we look at, so we said we fix the time, t, and then I want to know what is the displacement after, what is the particle displacement after a certain time t1. So then what we do is we consider the displacement of the bacteria along the trajectory, and then we do a histogram of those. So if the bacteria would behave like a Brownian particle, then this displacement distribution would be a Gaussian distribution. Because they are all, let's say we center all the trajectories to 0. Okay? So what you see is, so this is the distribution of bacteria. When they are non-motile, so this is like a passive type of particle. And what you see is, I mean, even though there is no motion towards the grains or anything, there's some retention at the origin. So what you see here is this black line. This is a Gaussian distribution, which we would have if this was a Brownian particle. And you see, so what we find is we find some skewness. There is a forward tailing And this we attribute to the velocity distribution, no? Because some particles have a high velocity, some particles have a low velocity, because we have a distribution of velocities in the flow field. No? So if some particles are on very low velocities, they are retained, and the particles are on higher velocities and they move faster. No? So this is an effect purely from the flow heterogeneity. It has nothing to do with motility. And then, so this is at the time 0.1 times tau v. This means the particles, they have not moved very much. So 1 tau v, 1 attractive time, means that the particles have in average moved over the distance of one of these pillars. Yeah? So here, they have not even moved over the distance of one pillar in average. But I mean, there's already some dispersion, of course, now because of the different velocities they have. But then, at a longer time, now when they have moved in average over 2.5, 3 of these gradients, then the distribution becomes, it looks more Gaussian. So now the bulk is adjusts better to this black line, which is Gaussian distribution, but not optimally. No? So here we get some backward, so there is no backward dispersion, which is simulated by the Gaussian. What I forgot to say is that these are data for all flow rates, no? From 18 to 197. All the 7 flow rates, they collapse on the same curves if we plot the distributions at the same dimension as time. No? This is why this is 0.1 tau v, 2.6 tau v. In absolute times, these times are of course different. No? Because for the slowest particle, this time is very big. For the fastest particle, the times are very slow. But still, they collapse all on the same curve, which is again a good sign. Because it says we can mostly understand the behavior of these propagators, of these distributions, based on the flow field. And then we look at motile bacteria for velocities that are in the higher range of the flow of the mean flow velocity. And what we see is, so here these symbols are the experimental data, and they are also again rescaled with the mean pillar diameter, and they are taken at the same non-dimensional time, 0.1 tau v and 2.6 tau v, and they more or less collapse, more or less not so well. I mean, you see here, let's say some big differences, and here some differences, and specifically in the tail. There are differences, no? So what happens here now is that these are bacteria that go towards the grains, no? That do this they have this high shear cracking, and then they move around the grains, and then at a certain time they detach from the grains. And this is, we have heard this is run and tumble motion, no? So they move and with the flow, and at a certain point they start to move the flagella, and they move out of the streamline. Here's the same. They move around the grain, and at a certain point they just take off from the grain. No, but what we see here is this trapping effect of the bacteria. And what you see here, the blue, this blue line is the model. The model I will explain a little bit later. This is the model for the non-motile bacteria. What you see here, the blue here. It's just to compare how different the spatial distributions are. Yeah. So now here, this is the same data as before for the high flow rates, and here on the bottom we have the low flow rates, and there is now also a qualitative difference whether we look at high or low flow rates. No? At high flow rates, okay, we get a trapping, but then we get a relatively pronounced forward tail. No? So some of the bacteria, they move fast, no? They move in pore channels. And a sizable amount gets trapped, not move towards the grains. And here, say the amount of bacteria that move forward is much slower. So here the flow velocity is so low that the bacteria, they just move everywhere. No? So they move towards the grains, they get trapped, they move around, and they do this much more often than in this case, no? Because the forward tail is let's say it's almost here. When you look at the lowest flow rate, this is when we are on the order of the swimming velocity, it's almost symmetric. Right? It's almost like a primary motion. So the model captures the data, so now I will explain you quickly the model that we have used. So we are using the continuous time random walk approach. Why? Because we have a medium. Well, let's do it the other way around. So when we, let's say the classical way of measuring trajectory is that you have a camera and you have a certain frame rate, no? And then you look at the motion at equidistant times. No? So the frame rate of so maybe photos per second, and this is your time scale, you know, it's the inverse frequency. And then you look at the positions always at the same time interval, no? After the same time interval. But this is not, let's say for an experiment, this is what you do because you have a camera. But if you want to describe the motion, this is not the optimal way to do it. Why? Because, let's go back. Because there's a structure in the medium, no? So here, when I'm in a pore, over a certain distance, the velocity is more or less constant, no? It doesn't change very much, no? So there is some persistence, there's correlation of the flow velocities. So this is why, from a modeling point of view, it's advantageous to model the motion, not isochronically, this means with a constant time increment, but equidistantly. No? So what we say is, this is a trajectory of a particle. And what I say is I model the motion of this particle by incrementing it always in units of the correlation length, not the correlation length of the velocity field. And this means, so this you have here, so all these crosses are equidistant along the trajectory. They are not equidistant when you project them to the x-axis, they are equidistant when you measure the distance along this curved trajectory. So this is how we move the particles in the longitudinal direction, and then we have the time of the particle. At each position, the particle is different time because the velocity changes. No? And this velocity here we obtain from the distribution of speeds, of flow speeds in principle. No? And so if the transport is by so what we assume is, for the non-motile bacteria, that the most important mechanism is attraction. The diffusion of these bacteria is not very big, and it's in fact very small, not because they are quite they're relatively big. And what we find is that the characteristic length scale that we have to use for this persistent length of velocities is about 2 times the grain size. And what we need for this is another detail is that the velocity that we need to use in this modeling framework is not the flow distribution, it's not the distribution of the flow speed, it's the distribution of the flow speeds, but weighted with the velocity. Yeah. So why is this? The reason for that is that when you measure particle speeds in this isochronic way, no? Where you measure every delta t particle speed. No? If you do this, then the histogram gives you the distribution of flow velocities. Yeah? But what we do is now we are not measuring, or let's say we are not sampling the flow, the velocities equidistantly in time, we do it equidistantly in space. So here, when we do this, we sample less low velocities than when we sample in time. It's clear? Not clear? No? So when you so when you have
switch on the light.
Then we have a trajectory, and let's say, so here we have a section with a very low velocity. No? So now in order to go over this section, we need a time L over V. No? So now I sample in equidistant delta t's. Yeah? So this means the number of sample samplings that I do is L divided by V divided by delta T. So if the velocity is very small, I sample this velocity many, many times. No, because I sample with a constant frequency. So this means the low velocities I sample much more often than the high velocities. Yeah? No? But when I do the sampling in space, I only sample this low velocity once. No? Yeah? So this is why I have to compensate for this sampling difference in the velocity distribution. So I have to fluctuate it. No? So when I do this sampling equidistantly in space, I have to compensate for the fact that this Eulerian distribution, let's say, oversamples the low velocity. So it's very important to use the right velocity distribution in your model, because otherwise you will not be able to make prediction. So now for the motile bacteria, we use basically the same approach. So we have the hydrodynamic motion, which is accounted for by this timing roulette, which is purely effective. But then this trapping that occurs has to be accounted for as well. And in this framework, it's accounted for by a trapping time. No? So what happens is, these are the pillars for the non-motile bacteria. They essentially move along streamlines. No? The non-motile bacteria. So the motile bacteria, they move along streamlines, but then eventually they just move out of the streamline and they go along the grains. And this they do for a certain time. No? So there is a characteristic trapping time by which they get trapped, and there is also a characteristic trapping frequency. I call it kappa. No? So they move along the streamline, but at one point they just get bored and they move out. No? They go somewhere else. But this they do with a certain regularity. No? This is why we model this as a rate process. No? So we model this whole trapping as a Poissonian trapping process. Poissonian means if there's a constant rate and there's a constant trapping time. So a constant mean trapping time. The trapping time is distributed exponentially. No? This is what you do when you don't know exactly what it is. The exponential distribution, because there's not much prejudice to it. No? But it's a good approximation. So in this modeling framework, one can show that a fraction of the trapped bacteria, and also you have bacteria that are trapped and bacteria that are mobile at any moment in time. No? So you have some fraction of the bacteria that move around the grains, and others they move in phosphate. And this modeling framework tells us that the fraction is just equal to the trapping rate times the trapping time, divided by 1 plus trapping rate times trapping time. And so this is what we did is we use this model and we fitted these parameters, essentially, the trapping rate and the trapping time. No? So the velocities, they are given by the velocity distributions that we have determined from the experiment.
That's the fraction that it could be reduced.
Yes, exactly. So what happens here is, there is no absolute zero time. No? So what is done in this type of experiments? Basically, you record pieces of trajectories. No? Yeah? So some bacteria they have long trajectory, others have a short trajectory, but you do this during the whole duration of the experiment. And in the end, what you do is you take all these trajectories that come from different times, no? And you center them at a zero. No, but there is no absolute zero. So the experiment starts, of course, this is the absolute zero, but then you measure trajectories all the time. Sometimes you lose the bacteria, then you find them somewhere else, you can stitch them together, the trajectories, but some you cannot, but then you take the second part of the trajectory and you count it as an additional trajectory. No? So what you have is you have trajectory with different initial times. No? Yes? So there is no absolute initial time, but what we do is all of them, we say, okay, the initial time is 0.
So you find if the tracking is actually possible. If it was not, then it would not be so.
No, so the thing is, but it's intuitive that it's possible, because what happens, we have a medium which is relatively regular. So, what happens is, they are moving along, the bacteria. So you have a characteristic distance, so there is nothing fractal, anything, there are no huge distances between these pillars. And then also, this bacteria, this run and tumble motion, this happens more or less like a Poisson process when you look at it at a free fluid. But this is also debated. There are also measurements that say this Poissonian assumption is not good, and the trapping time distribution is not necessarily exponential. But most of these studies are for free fluids, not for porous medium. So now, exactly, so there is no absolute time 0. So this means when you take all these trajectories and you mix them together, the whole system is in equilibrium. So this is why what we do is we start with the equilibrium distribution, and this is very good, because this is what we see. No? So there is no. So for example, if you would say you start at absolute time 0, all the bacteria are of course mobile. They are motile. No, nobody is trapped, because you just introduced them in the system, and then you would have an initial fraction that would be all motile, and then only with time they go towards an equilibrium. But here, since we are in an equilibrium situation, we have to account for this now. So in the model, we directly start with the equilibrium fraction. And then, what we need to fit is, we need to fit these times and the trapping rate, but what we see is the time is inversely proportional to the velocity. No? Because we have 7 different flow rates. This is what we get from the data. It's also intuitive somehow. But is it intuitive? No, it's not so intuitive. Yeah? So when you increase the flow rate, it is. When you increase the flow rate, the trapping time decreases, because what happens is, shear is good on one hand because it brings, because the bacteria like to go to the high shear. On the other hand, the shear also can, how to say this? So when the bacteria is close to the grain, you have a very high velocity, it takes the bacteria with it in the flow. No?
So that means they don't do anything actively to avoid being taken away, in a sense. Right?
No, not only this, they also move away voluntarily.
But it sounds like, so if they were trying actively to stay there, I would expect sublinear.
You would expect so.
Sublinear. Right? Because of the activity.
So what we find is this now, it's more or less inversely proportional, and the trapping rate is proportional to the velocity. Yeah. So this is maybe not so intuitive, but what happens when you filter something through? You get a higher velocity, you have more particles that you have retained. No? Detailed.
I think we have to define a zone which means being trapped.
No, exactly. So this is what you need to do when you want to measure it from the experiment. Exactly. So this is the paper by Adama Kelly. No, here, not in this model. No, exactly. No, in this model, the only thing that we have is we have a trapping rate and a trapping time. These are the 2 parameters that account for the motility. And then we have the distribution of velocities, which accounts for the hydrodynamics of the porous medium. Also, it's a good point. No? So it's not we don't define what is the radius of influence, no, or what means trapped. But the paper by Adama, so when they did the measurements, they had a model like this in mind, and they said, I want to measure the trapping rate, I want to measure what is the characteristic time. And then they had to define the radius of influence. But of course, all the results, they are very sensitive to the definition of this radius. So what is immobilized, what is mobile?
You now get it through this row.
No, exactly. So in this model,
just one parameter.
Exactly. So we have a model, it's of course idealized, And I said we have two parameters, and these two parameters they tell us essentially what the bacteria do in average. No? And right, so yeah, and let's go back. So yeah, you see, let's say the model works relatively well. Now it can capture the data with all flow rates, and it allows us also to make a prediction for longer times. So here in the data that we have for the trajectory, they are only good maybe for 4 or 5 attraction times. No? Because then you lose in this technique, often you lose the bacteria. That's it. Now, when the bacteria are very fast, then you lose them earlier, no? Because they go out of the field of view. And so with this model, we are able to do extrapolation, let's say. So this would be the velocity of this would be the mean displacement of the non-motile bacteria. Everything is linear. And then this is the mean displacement for the high flow rates, bacteria, for the bacteria at high and for the bacteria at low flow rate. So you see there's a retardation. So this is basically a classical colloid filtration model, which tells you get a retardation of your colloid or bacteria. The retardation coefficient is just 1 divided by 1 minus rho. No? Rho is the fraction of immobilized particles. But what happens is the dispersion coefficient can be larger. No? So this is the variance, the displacement variance so the black is again the non-motile, and the red is the non-motile at low flow rate, and the green is the non-motile at high flow rate. So it's the motile at high flow rate. You see here the bacteria are dispersed even faster than the non-motile. So the retardation acts on the mean displacement, but regarding the dispersion, it gives actually the opposite effect. But this is also intuitive because what happens here, you have a chromatographic dispersion effect. So some bacteria go to the brain, other particles move on, so you get a bigger dispersion. But there is a threshold. No? If the immobilization is too big, you're retaining many more bacteria, and then so this happens at around this flow rate. No? So here. Yeah, so here you have a qualitative difference in the retardation factor. The retardation factor tells you something about the mean displacement. And then we looked at the dispersion coefficient for the motile bacteria versus non-motile. And what you see is that for a certain fraction of immobilized particles, you get a larger dispersion effect, but when you start immobilizing more and more, which is what happens at low flow rates, then at one point you get also retardation in the dispersion. No? So basically we have a grouping of the behavior of the bacteria for low and for high flow rates. So that's a qualitatively different behavior. And with this, I conclude. So we have so we could capture the impact of hydrodynamic fluctuations and motility using this CKW model combined with a Poissonian trapping. And we find that the dispersion and the trapping mechanisms, they all scale with the flow rate. Yeah? And which is interesting because you could also think the bacteria, they just swim and it has nothing to do with the flow, no? The trapping or so, but there is this interaction, and then so we have data is grouped into families, and bacteria motility can do both. It can either increase or it can enhance dispersion depending on the flow rate. Thank you.
Thank you very much. Questions?
How is the concentration of bacteria?
So here it's more how many bacteria. I think so. Here it's more how many trajectories. So I think it's 10,000 trajectories.
Because and you see some of them get attached clearly but never recover.
No, they're on.
Because normally they used to get attached from the biofilm.
No, here not.
Why?
No, here. But here, so this experiment, I cannot tell you details, but it was intended to have exactly not the conditions that I found biofilm.
And the material of the pillar is what?
It's a PMM, some plexiglass.
Maybe for that, because they can look at
Yeah.
No, because I get surprised that you don't see any
Yes.
clues of
No.
mass
They
appearance.
swim to the high,
To the high shear.
shears of the.
Yeah, but I guess normally they swim there to get attached from the biofilm and get advantages. So
Yeah, but yeah.
What's the bacteria?
Huh?
What are the bacteria?
E. coli.
So, do I call it in there was some most of them can get strains that have these things knocked out, so they can.
I think
Yes. No, but we can do it in paper by Adama. It's in explain on the experimental details.
So, as you were saying, these guys are PTB, so they don't disperse very well, diffuse very much in the ground emission sense.
Yeah.
But in the very low flow rates, you see that you have this dispersion.
It's called radial diffusion. It comes from motility.
So they just swim backwards and you know.
They swim forwards, but it's a random motion type of. It's not totally random because when you look at the displacement variance, you have this ballistic behavior, very short times now. So they move in one direction persistently. So often this is modeled by an scientific process.
So basically, in your team, you never have backwards motion.
In the model not. No, the model, but of course you see it, and with the model we cannot reproduce it. No?
So you say that in this case, in the very low flow rates, it's obviously more important, and you say it comes closer. It's more clear here, right, like the process.
Yeah, I don't know here exactly. See, I mean, there's a lot of backward motion. Even here as well, which we don't really pick up with the model because in the model everything is forward.
But then, of course, as you increase the flow rates, it's not right.
Yeah, because you push them out.
You seem like too much for diffusion.
I have a question. This row is a constant, or does it depend on the flow rate?
No. Well, you see, so it does not depend. It does not depend on the flow rate. Exactly, very good. See, because it's gamma times it goes with gamma. It goes with the flow rate. Tau C is the inverse flow rate. So here you have the product of the two. So it's really not dependent on the flow rate.
So actually, what you really, your actual parameters are the 1000 gamma. You would say.
Yes, it is tau gamma. But the thing is like this. So for the rohr, there seems to be a threshold. No? So for high flow rates, we have a value of rho of about 0.3. For all the flow rates with a mean velocity larger than 98, and for all the lower flow rates, we can fit everything with a single rho value. This is in fact how I did the fitting. No? So I fixed the rho value.
Okay, of course, if C goes very large, because then it doesn't depend on tau C.
No, but I mean, if this thing becomes very large, the rho is equal to 1.
Yeah.
Not this is little. No, but I mean, the thing is, so what we fitted, we did not fit each data set individually. So we fitted the scale data. So the fit that you see here. So we didn't do a fit to each of the 7 data sets. We did a fit on the rescale data. So this means it's the same values for all the data with a flow rate that is larger than 100, and we have the same parameters for flow rate smaller. So this is it. So this is why this is interesting here. That on the one hand we have flow rate dependence on the trapping and the trapping rate and trapping time, but then we have this rho, which is not flow rate dependent because it depends on the product of the two. But then it is flow rate dependent because for high flow rates it has a different value than for low flow rates. So there is something in the bacteria behavior that changes depending on the flow rate.
So it's
Huh?
So I was just saying that means that the governmental C are not quite always.
Yeah. So let's say the prefactor of this figure depends on the flow rate.
I suppose if you have another flow rate, another velocity thing, and you also have this shear thing.
Yes.
It's different.
Yeah. No, I mean the thing is to have this grouping of the behaviors for high and low. No? So that there seems to be a threshold. Now, if the flow rate is too low, then the bacteria they can move freely. Also, they are not disturbed, let's say, by the flow so much. And if the flow is too high, then they are taken away.
Yes. Okay. I don't know whether there are more. Let me see the people online. There are questions of people online. People online who wants to say something, they can do. I don't know, someone else. People online. So.
Just you're here.
Someone else want to say something? If not,
Well, maybe just, sorry, Martin.
yeah.
I have some problems with the audio and I couldn't follow the discussion on the whiteboard, but basically Marcos, you modify the dispersion coefficient in order to fix the data according to the velocity. So you can more or less.
Look at the camera.
Pablo,
Yeah.
we didn't fit the dispersion coefficient. Now we fitted only the trapping rate and the trapping time, and we fitted them to the full data set simultaneously. This means not to each data set separately. And then from these values we can estimate the dispersion coefficient.
Okay. So just one suggestion, it's difficult to follow the audio. Maybe you can consider to buy a microphone for the room or something like that. There's a lot of echo.
This was a comment for you.
Sorry? What did you say?
Buy a microphone.
Maybe it's a good idea.
We have problems with that. I mean, it's difficult enough to do this online, etc.
Presencia in the place.
Yes, true.
Okay, sorry.
Okay. More questions? If not, thank you for attending. Thank you, Marco, for your presentation. And that's it.